Dear student, welcome to my channel. Topic of this video is logistic regression. This is the second video on this topic, and in this video I am going to explain gradient descent algorithm for logistic regression. Now let us start. In logistic regression, y cap, that is nothing but predicted value, is a non-linear function, that is nothing but sigmoid, and which is given by the formula y cap is equal to 1 upon 1 plus e raised to minus z. If we use this in the mean squared equation, that is loss function or objective function, then we will get a non-convex shape with many local minima as shown in this figure. So when local minimas are there, then high chances are there that algorithm will stuck up here and it will never converges to the main point, that is nothing but the global minima. So when we are using this function, that is the mean squared function with non-linear, then at that time it will create a problem. So we require one function which is a convex in shape and having one global minima, so no chances of the local minima. So to do this, we derived a different cost function or logistic regression called log loss, which is also derived from maximum likelihood estimation method, and formula for this is nothing but the record summation 1 to n yi minus yi into log of predicted yi plus 1 minus yi into log of 1 minus predicted yi, where yi is nothing but the function which is non-linear in nature because it is using sigmoid function, so it is represented in variety type of way. So in derivation, either we are using y cap is equal to sigma z, and when we are making the derivative, at that time we are expanding step by step. So this formula is come from basically from the Bernoulli distribution. Now we will see how this formula derived. In logistic regression, we assume a binary outcome with each outcome being either success or failure. For Bernoulli distribution, the probability mass function for a random variable y that can take either value 0 or 1 is given by, so p of y, where y can take the value between either 0 or 1, it is given by p raised to y into 1 minus p raised to 1 minus 1 minus y. So p is the probability of success and 1 minus p is the probability of failure. So here y is either 1 or 0. So same formula we are using for the log loss. So this formula provides the probability of observing a specific outcome. If y equal to 1, then it becomes p, which is the probability of success, and when y equal to 0, so this becomes this answer becomes 1 minus p, which is nothing but the probability of failure. So we are using the same formula to derive for the log loss function, that is nothing but this formula. In logistic regression, we assume that the response variable y follows Bernoulli distribution, whereas the probability of y is given by this logistic function. So in logistic function, we are using this formula, and this is again represented by sigma z also, and which is nothing but basically the probability of success. So here we are just simply replacing this formula by this, that is p of p raised to y, it is given by sigma z raised to y and 1 minus sigma z raised to 1 minus y, and the formula becomes like this as we have n number of records. So this formula becomes, that is a product of sigma z raised to y into 1 minus sigma z raised to 1 minus y. So this is the loss function. Log loss is equal to, it is represented by L beta, product of sigma z raised to y into 1 minus sigma z raised to 1 minus y. And here if we put this sigma z, which is basically nothing but sigmoid function, it is this. So to make our calculation easier, we multiply log on the both sides. So we are taking the log on the both sides. So when we take the log, this product operator converted into the summation. So it is summation 1 to n y into log of this plus 1 minus y into log of this operator. So this function we will get called the log likelihood function, or the sum of the log conditional probability. In machine learning, it is conventional to minimize a error function via gradient descent rather than maximize objective function via gradient ascent. So to understand the further part, it is very much important to understand the gradient descent or how it works. So if you understood or you already know how the linear regression with gradient descent, then the further part is very easy to understand. If we maximize this above function, then we will have to deal with the gradient ascent. To avoid this, we make negative of this so that we can get the gradient descent. So this is basically equation which maximizes the probability. So this is a gradient ascent function, but we want gradient descent function to get the global minima. So we require to convert this function into the minimization. So this is our function which is maximization, that is gradient ascent, and we are taking minimum of minus log x. So by this way it is converted into the minimization function. So that's why this negative sign comes here, and that's why we have seen that in the first formula. So this is the formula in which we are taking the minimum of minus log x for the minimization problem. Now minus log L of b is equal to minus 1 by n y into log of alpha z plus 1 minus n log of 1 minus sigma z, not alpha, sigma z into log of 1 minus sigma z, where sigma z is a sigmoid function. Then here we require to see that by using this function we should get the convex shape with one global minima. So we will see that why we are getting, when we are using log loss, why we are getting this convex shape one with global minima. Now we will see the two cases. Here y is nothing but the actual output and this is a predicted. Here again y is actual output and this is a predicted value. Now y can be either 1 or 0 because it is a in class data set, the class level is either 1 or 0. So we will take the first case when y is equal to 1. So when y is 1, the first part is active, and 1 minus 1 is 0, so second part is not active. So when the first part is active, so this log of sigma z, this is nothing but the sigmoid function which vary between 0 to 1. So we will take the maximum value. Now we will see that if this value is maximum, that is 1, then we are getting log of 1 is 0, so we are getting a 0 value. So when this value is 1, we are getting the 0 value, and when this value is 0, log of 0 is infinity, so for this 0 we are getting that infinity value. So we are getting that first half part. Now we will see when y is equal to 0. So when y is equal to 0, this part is not active, this part is active. So here 1 minus 0, then this value can be 0, this value can be 1. So when this value is 1, then at that time log of 0 is what? Infinity. So when this value is 1 and this value is 1, that is 1, so we are getting the infinity. And when this value is 0, at that time we are getting the log of 1 which is equal to 0. So when this value is 0, that is means this value, we are getting log of 1 and log of 1 is 0, so we are getting this part. And when we combine, when y equal to 0 or 1, at that time this is the half part and this is the next part. So when we combine, we are getting the convex shape by using the log likelihood function. So that's why we are using this function. With this function we achieve the convex shape and at the same time one global minima, so that either we start from here or here, we will reach here by using the gradient descent, as same as in the linear regression. Now we'll see the gradient descent formula. Gradient descent formula is x of I plus 1 equal to xi minus alpha f dash x. So where basic function is f of x, and in this function the parameter is x. So we are changing the parameter value, that is this is the new updated value of the parameter. X of I plus 1 is equal to x of I minus alpha, and here we are taking the derivative of this function, that is nothing but f dash x. So when we use the derivative, we are start either from here or here, and we with the alpha we are making the steps to reach this global maxima, global minima, because this is our minimization problem, because we want to minimize the error between the predicted value and the actual value. So here in our equation, the beta 0 and beta 1 are the parameter. So we require to take the partial derivative with respect to beta 0 and beta 1. But here direct derivative is not possible. So here chain of derivative is there. So just see this equation. This is a basic equation minus summation 1 to n y into log of sigma z plus 1 minus 1 into log of 1 minus sigma z. Now sigma z is nothing but the sigmoid function, which is represented by 1 divided 1 plus e raised to minus z. And here for simplicity we are replacing this sigma z by p, so that derivative operation makes easier. So we are just replacing this by sigma z by p. So y into log of p plus 1 minus by into log of 1 minus p. Now we are taking the derivative. So here we require to take the derivative. So we first require, this is the original function, that is log L of beta. So we first take derivative with respect to beta 0 and beta 1. But here directly derivative cannot be possible, because we require to take the derivative with respect to of this term. Then this term is with respect to p is nothing but with respect to z, and z is nothing respect with the beta 0 and beta 1. So first we will take the derivative of this term. So it becomes y divided by p plus 1 minus y divided by 1 minus p. So this is the first part. Then we take the derivative of p with respect to z. So this is the way p is equal to sigma z, which is nothing but 1 divided by 1 plus e raised to minus z. So derivative of this is nothing but p into 1 minus p. So this is the formula for derivative of this. So derivative of this term is p into 1 minus p, that is nothing but this term, but this term is nothing but p into 1 minus p. Now we take the derivative with respect to z. Z is nothing but beta 0 plus beta 1x. So we take derivative with respect to beta 0 and with respect to beta x, which is nothing but 1 and x. So this is our gradient equation, that is updated value of parameter is equal to current value minus alpha L, that is loss function of that beta. So here we are taking with respect to beta 0 and beta 1. So as such there is no difference. For beta 0 1 is there, and for beta 1 only x parameter gets not x value, x coefficient get multiplied, it is not parameter. Now here first we will see the another case when y divided by p plus, because when we take all chain derivative into the multiplication format, so it becomes y divided by p plus 1 minus y into 1 minus p. This is the first derivative. Second derivative is p into 1 minus p, and third derivative is either 1, or for the beta 1 it is a x. So y into 1 minus p plus p into 1 minus 1, this and this get cancelled, so we are getting this value. So this value is represented by this y into 1 minus p plus p into 1 minus y is represented by this value. So I will explain why it is represented by y minus p, and as negative sign is there, so it becomes p minus 1. Similarly for beta 1 only x parameter is different. Here it is 1 and here it is a x, not parameter, it is coefficient. And for this again y into 1 minus p, p into 1 minus y, and this is cancelled. So we are again replacing this by this term. So this y into 1 minus p plus p into 1 minus y is represented by y minus p. So reason is that for this equation either y can be 0 or 1. So when y equal to 1 we are getting 1 minus p, and when y is equal to 0 we are getting the p. So depending on the value of y, the expression either becomes 1 minus p or expression becomes p. So what is the idea behind the y minus p? The gradient y reflects the error in the probability space. So when y is equal to 1, the gradient becomes 1 minus p, which pushes p closer to 1, and when y equal to 0, the gradient becomes p, and which pushes p closer to 0. So this is the direction we want to adjust p in order to minimize the cross entropy or log likelihood loss. So initially it is very difficult to understand, but when you implement at that time you will come to know that what happens when I equal to 1 and y equal to 0. So this is the final equation. For one is for beta 0 and second is for beta 1, but as such only difference of x is there, so I have represented equation of only with respect to beta 1 parameter. So this is all about the derivation of logistic regression using gradient descent. So initially it looks difficult to understand, but if you know the gradient descent with linear regression, it is very easy to understand the concept behind the logistic regression. Thank you.